Hey, welcome to the first part in integration. It's called the Fundamental Theorem of Calculus and the Rules of Integration. Have you seen some of this before? If you've been watching this series of presentations, you would have seen this back in Modelling and Introduction to Calculus, Introduction to the Fundamental Theorem of Calculus, where we're looking at upper and lower sums, and ultimately trying to look at the area under the curve, and that's what we're going to be doing now. We're trying to find an expression for the area under the curve, and this little adventure is going to be called Searching for the Fundamental Theorem of Calculus. It's an interesting piece of mathematics, so hang on in there and come on down and let's get going with this idea. So here we have a little bit of a summary of what we did before. If you haven't seen this before, it doesn't matter. You can join in now. What we're trying to do is to look at the area under a curve. Area under a curve. And this has got lots of applications. And if you have a velocity time graph, of course, the area under the curve is the displacement or the total distance travelled there. Let's have a look at how we might do it. Well, first of all, we could draw in all these rectangles. See that some of them are above the figure and some of them above the graph, and some of them end up under them. So we could sum up there the upper area sum of all those taller than the actual area under the curve is the sum from I equals 1 to n. We're going to do n of them along here. Sum from I equals 1 to n of how high are they? Well, how high is any y value under a curve? You substitute in the x and you get f of xi, whatever x value you put in there, sub it into the function y equals expression, and you'll get the height under that curve there. The y value is the height under the curve there. And then we multiply by delta x. So this is length times breadth or something, if you like, for a rectangle. Delta x means the small gap between, or the width of the rectangle, small gap between the rectangles, or width of rectangles. Let's come over here, and what have we got here? We've got a lower area. That's the area of all the rectangles that just come up and touch but are underneath. They're still using the y value on the left there to create a smaller rectangle, smaller than the actual area under the curve. So let's sum them again from I is 0 to n take 1. Can you see that these will stop short of n because you can't go another one? You're under the curve here and you're stopping here at b, the n rectangles, so you'll go to one width less there. So you'll do the same thing. The function value, how high is that lower rectangle? Substitute the x value into the function to get the height, the y value to that lower point on the curve. And then multiply by the width of the rectangle. Do you see it? Can you see that the actual area is going to be bigger than the lower sum and less than the upper sum? Somewhere in the middle here. Okay, because the lower sum leaves gaps underneath and the upper sum's got these above. So the actual area shaded there, very rough shading, mate, is somewhere between the two. There it is there. Okay, that's what we're trying to do. The exact area between the curve and the x-axis from the x values A to B. And we're drawing in n rectangles and trying to estimate it. Okay, do you reckon we should increase the number of rectangles? Come on down and let's see what happens when we do this. These are screen clippings from Hayes and Harris here, and that's a good textbook to have in this particular course. Okay, let's have a look. What are we doing up here? These are all the lower rectangles. See, they're underneath. And there's getting more and more of them. More and more. Up to 50 rectangles from 10. What's happening? Oh, you could say they're all becoming one mass. They're integrating into one mass, if you like. What about the upper rectangles? 10 of them, 25 of them, 50 of them. What's happening? Getting very close to the same thing. The upper area and the lower area are almost becoming one whole, one mass, the same. And this is where we're going to start the word integrate. The two approaches, if you like, are integrating, becoming one. And we still have this though, the areas jammed between the upper area and the lower area sum, but G, as n tends to infinity, as a number of rectangles approaches infinity, AU is approaching AL, they're becoming as one, they're integrating into one. Hey, this is where that word comes from, I think. Anyway, come on down, let's do some more. And here we have a result, a couple of results here. First of all, what we're going to say is this thing up here. As n tends to infinity, the upper area approaches the lower area. So we're going to say the limit as n tends to infinity of this sum is going to be one whole mass. They're going to approach each other. So we're going to call it this sign, which we call the integral. The integral from a to b of the function. We've seen that before in the introduction to the Fundamental Theorem. And we call that the becoming of oneness, if you like, of the upper and lower sum as n tends to infinity. We actually haven't found a value for this. How do you calculate this? This is a symbol only representing the infinite sum of all those rectangles from A to B. And of course that's why the integral sign is like that, isn't it? It's a stretched out S. For what? To remind us it's a sum of rectangles, upper and lower rectangles, taken in an infinite way to approach this area. So this is the actual area represented by this symbol from summing an infinite number of triangles, making them become one, the upper and lower become one. And how are we going to do this? This is exciting, but can we find a formula, a way of calculating this? We have a symbol, but we don't have a way of actually calculating that tendency of the infinite number of rectangles to produce one integrated value. So this symbol here, this sort of thing, is full of mathematics. It's important that you see why we've chosen integral as the word for this process and why we've chosen the skinny sign, which is standing for an S. Exciting mathematics. Let's come down now, and this is what we've come to. We have a symbol. If f of x is a continuous function, so there's no asymptotes or anything in it here. This is a continuous graph. There's no breaks, no discontinuities, no breaks at all. And across the interval from A to B, what we're going to do is try to sum, there it is, sum an infinite number of rectangles across there and get the area. And that is representing that. If only we knew how to calculate exactly an infinite number of rectangle sums. Oh, well, that's not going to be possible, is it? No, not with that approach. Infinity. Can't ever do an infinite number. That's what we're going to pursue in this unit. Exciting stuff. Okay, let's go down and have a look. So we're going to define A of t, that is the area from x is A to x is t. Can we find this function? And of course we're going to put it equal to integral from A to B of f of x dx. If we can find it, there's our symbol for the process. What will the function be? Can we find that function? Okay, let's define some stuff before going on and trying to find it. Let's define A of t as the integral summing an infinite number of triangles from A to t, so they become one. So remember, that's a word because they become one. If you integrate an infinite number, it becomes one whole mass. Then we're going to say this represents that in there. We're going to integrate from A to t, make a one mass of an infinite number of triangles and sum them. And we would have A of A, of course, would be naught. Because we're going from A nowhere. We have no interval in which to divide up into an infinite number of rectangles. And A of B, of course, would be integral from A to B. Okay, we're defining A of t as our base function, starting at A and going to t for the infinite rectangle sum. Have you got it? Let's go and see if we can do some maths and see if we can find a way of calculating this function. This function which is going to integrate all those rectangles, infinite number of them. Come on down. It's getting exciting. Here's the first bit of our derivation. So I'll just put all this up there for a start, I think. Just go to there. Oh, hang on. We'll come back. Let's go to that bit, I think. Okay. Now, let's take the function and let's take a narrow strip of area. So it's from the x value of t to the x value of t plus h. So what can you say the width of this is? It's h, isn't it? So this is t and t plus h. So that rectangle drawn there has a width of h. Okay. Now, in our definition of our function, it'll be a of t plus h, take a of t. Because a of t plus h, remember by our definition just above there, is the area from a to t plus h. And a of t will be the area from a to t. So that's the area of the strip. Now let's go and pursue this. Because if we can find an actual expression for this, we have a chance of really uncovering what this function a, which gives us the infinite rectangle sum between a and t here, will actually be. Let's go down. Okay. So let's come down here. Now, what's the area of the smaller rectangle up there? So here it is here. The smaller rectangle is constructed at t. So its y value up to the lower point on the curve is sub the t value in f of t. So what's its area? H times f of t. And our actual area function in the middle is somewhere between that lower rectangle area and the upper rectangle area, which is, what height's it got? F of t plus h. Still by a width of h. So this is the area of the larger triangle. Now, our difference function, giving us our strip, is a of t plus h, take a of t. So that value lies between these two. Similar to upper and lower rectangle sums before. Now, let's divide everything by h. And so we get rid of there, h is tending to naught but not equal to naught in a minute. So we get that. Hey, this looks familiar. Does it to you? If we take the limit as h tends to naught, what is that? That looks like a first principles derivative definition. Limit as h tends to naught of the middle expression. Hey, it is what? Here, a dash t, isn't it? From first principles. I come up right up the top here. I just want to revise that. F dash x is the limit as h tends to naught of f of x plus h. Take f of x over h. First principles definition of the derivative. That looks like it's just a function there. We want to have f dash of x. Remember that. Gee, we've done it. Have we? What have we done? It's rather puzzling, but we're saying the derivative of a is jammed between f of t and f of t. Why? Well, if h tends to naught, this value, f of t plus h, tends to f of t. So we've got the derivative of our unknown a function, which will give us that area, is between f of t and f of t. What does that mean? This is confusing here. Well, that's called the Sandwich Theorem. If you have h tending to naught and two ends of an inequality both approach each other, then the thing in the middle, by the Sandwich Theorem if you like, has the same limit. A of t will also equal f of t. The limit will be f of t. Both ends are tending to f of t, and a dash t will therefore be jammed in the middle. A dash t is f of t. What's that? Our area function is a function such that if we take the area and differentiate it, we get the function we're trying to find, the area of the curve and the x-axis. That area between the two is a. Does that make sense? Let's have a closer look at it. To get the area under a curve now, under a curve of f of t, we have to find a function which when differentiated will give that. We've got to go back here We want the antiderivative. We want a function which, when differentiated, will give f of t. And that's our area function. That's confusing. We've got to go backwards with differentiation and find a function which, when differentiated, will give our function, and that function there, will, when we sub into it, will give us an area. This is magic. Didn't think it would work out that way, that when we're trying to sum an infinite number of rectangles under the curve, that it had anything to do with the derivative. But we know the function that will do that is a function such that its derivative gives f of x. Can you see it? We're going to have to do the reverse of differentiation to find this function. Okay, come on down and let's see what we can do. Here's the summary of it all. For a continuous function f of x, there you are, which you want to do a summing of an infinite number of rectangles or an integral for between a and b. So this is actually called a definite integral. You're going to do a definite number of, or area under the curve, infinite number of rectangles between a and b. What do? Well, to actually do this, we need to substitute the b value, the second point. Let's do this now. Here, a to b. What we're saying is we've got x and y. This is from some function. Then we want the function up to from a to b. It'll be the function value of b minus the function value of a. What function? The function which is, or which has as its derivative the original function. So we need to go back to find our area function into which we're going to substitute b and a to find that area, or to find the sum of an infinite number of rectangles integrating one whole mass. We're going to have to find the antiderivative, the function whose derivative gives us f of x. It's an interesting toing and froing here. Let's do something with it now. You can say, well, I can see that we could apply this to our motion problems from before, like we did, if this was velocity and time, and we were doing this between 2 points in time, finding the integral or the infinite rectangle sum. All we'd have to do is find a function whose derivative was v, because this is our function here. V is our function. V is a function in t. And what function has v as its derivative? It's s, isn't it? S dash t is v. So what we would do is substitute T2 and T1 in there to subtract that, and that would give us the displacement under the curve, under the velocity time graph, because the derivative of s is t. Let's go on and see if we can do some more work with this idea. Here are some results. If we're going to do this, can you see the infinite sum from a to a, that's nowhere on the x-axis, will be 0. If you had c times it, and I think this is a question coming up down in the first question that Hayes and Harris asked. I'll ask you to think about the rest for yourself. But here, what would this mean if you have a constant there and you're integrating it? What does that mean? The function is constant, so y equals c. So what would be the area then? Well, can you see that is going to be c of b take c of a, okay, or c of b take a. If you like to find the antiderivative of c, because that's what we're trying to do, what function which when differentiated gives c? It's cx. And if we did that from a to b, it's cb minus ca. So we can work through it in that way. Here we're doing the sum of two different regions, the sum of the two definite integrals, or here, infinite number of rectangles. So that's going to be the simple sum across the region. We'll have a look at a question in a minute where you're asked to try and look at this graphically. And if you reverse the positions, Why would that be the negative of a times b? And if you multiplied the function by a constant, what would that all mean about the infinite rectangle sum? Infinite rectangle sum, which is infinite, going to give us an integration, a whole mass of rectangles. And similarly, down the bottom. So I want you to think in a minute geometrically about that. So come down and let's have a look at that question. It's being done here. I've got one here done for you from Hayes and Harris. Infinite rectangle sum from A to B plus infinite rectangle sum from B to C. Why does it represent the infinite rectangle sum across the whole region? Well, let's have a look. Let's do it with the fundamental theorem. If we say f of x has an antiderivative called big F, right? So in other words, big F dash x equals f of x, we can use this as our area function. We can sub in f of b, take f of a, that would be across the first region, and that would be our way now. Remember the antiderivative, our area function is the antiderivative of our function. That function, which when differentiated will give our original function, and then we'll evaluate it at c, f of c, take f of b. Okay, so they're going to cancel out, and you're going to have f of c take f of a, which of course is the integral from a to c of f of x dx from before. Or over here, doing it graphically, there's two ways. This is how to do question 1 coming up in a minute. We're trying to prove this result here, that you can sum over two regions. Here we're doing it graphically, saying the first infinite rectangle sum is that and that, so it's a1 plus a2, and that would be the same as doing an infinite rectangle sum across the two regions. Okay, so you can either do it over here algebraically with the fundamental theorem, once you know the antiderivative, okay, that function which when differentiated gives the original function, and sub into it. Alright, come down and I want you to think about these. Use the fundamental theorem of calculus to show that that's true and explain the result graphically. You can try to do each of them by substituting into the fundamental theorem. Remember, a of b, integral from a to b, infinite rectangle sum under the graph of the function f of x is equal to the antiderivative evaluated at the second point minus the first, where f dashed x is f of x. So you've got to treat f of x as a derivative and come back and find the function which, when differentiated, would give it. But we're not into that right at the moment. We're just into the general functions here. We can't actually find the antiderivative. We will just let it be big F of x, and play around with some expressions and some graphs as well. Think about what we're doing with the infinite rectangle sum, with rectangles under the curve, between the curve and the x-axis. Okay, come down now. There are the solutions, sorry, so I've skipped that too quickly. So come to there. There are the solutions. I've split it up this time, question by question, make it easier for you to travel through there. Okay, let's go down and have a look at an example now. Alright, use the fundamental theorem of calculus to find the area between the x-axis and y equals x squared from x is 0 to x is 1. Let's draw a graph. Always draw a graph. You can use your graphics display calculator to do that, and then we'll have a look. So what are we going to do? Well, first thing, we know the representation for the area is the integral sign, representing a sum, a skinny S sign, sum of infinite number of rectangles from 0 to 1 of x squared dx. Yes? So we know that would give that area. Looking at it, checking it. Yes? But how do you do that? Well, we have to find this area function, which is such that its derivative is the original function. Well, let's go back and find it. If a function was x squared, what function would have its derivative equal to that? Well, let's reverse the x to the n rule. We know the derivative of x to the n is x to the n, n x to the n take 1. Hang on, I've put that around the wrong way there a bit. So derivative of xn is n x n minus 1. So if you want to go back and create the function from a power, what will you do? You'll increase the function, increase the power by 1, so there'd be x to the n take 1 plus 1, and divide by the new power. So this would be x to the n, it would cancel there, give you x to the n back again. So what's the rule that we're going to use here? Increase the power by 1. Okay, increase the power by 1, so let's do it there, and that'll be 3, and divide by the new power. And we can check it by differentiation. Let's differentiate that. Derivative of this is a third. Derivative of x cubed is 3x squared. So that's a process we're going to be faced with a lot now. We have to find that antiderivative. The function is here, and we've got to go backwards and find what function when differentiated would give it. And now we can sub in, if we've got that function. We actually know how to calculate this. This is calculable. The infinite rectangle sum, the integration of all those upper and lower rectangles. So when we sub it in, put 1 into, well, we really should have a working line here which goes like this. X cubed on 3, and we'll evaluate it from 0 to 1. So stick 1 in there, becomes a cube, 1 cubed over 3, take 0. 0 cubed over 3 is 0, so it's a third square units. What about the next one? Root x. So what is the area? I'd like to do this first. Infinite rectangle sum from 1 to 9 under the curve. Alright, but to do that, the area function is the antiderivative. That function, which is the derivative of the given function. So here we are, it's x to the half. That's an x to the n rule. Increase the power by 1. X to the 3 over 2, a half plus 1, 1 and a half, or 3 over 2. Divide by that new power, and there you have a function. You can leave it like this, or put it in this form for substitution. Let's just check that. Does that work? X to the 3 over 2, this is antiderivative, all over 3 over 2, is 2/3 x to the 3 over 2. Let's check that now. Let's differentiate that. D by dx on the wrong side there, mate. Let's check it. It'll be 2/3 multiplied by n x to the n take 1, which be half. Yes, it works. It comes back to root x. So you can check the antiderivative by differentiating. We're going in reverse now. This is going to be a bit confusing. Going backwards. Integration. Integration. Oh, making whole. Sum of infinite rectangles. But what is the process? It's anti-differentiation to find that function. So once we've found the function, there it is there. That's simplifying x to the 3 on 2. Let's just check that. It's x equals x to the 1 times x to the half. Or x times root x. Make it easier to substitute in. Let's substitute in 9 and then 1. So here are the two evaluations there. Oh, you're going to have to keep your head straight here on this one. We want a function whose derivative is that function, is the original function, to get the area under its curve, going backwards. And of course, you can do it on the calculator. So come down with me now, and I want to show you how to use the Casio in two different ways to find the area or the definite integral there. When we put in definite numbers called the definite integral. So, here's the first way. You go to run mode. Here it is over here. So, you go to menu, highlight run and go in there. So, in run mode, now, what you need to do is to hit options. Here it is here. Can you see it? Options. And if you hit options, you get this window here. Here's some options for you. We've used this for matrices before. If you're doing other subjects, you might have used complex numbers, but this is the one we want here, calc. So hit F4, and when you hit F4, you get these calculation options and more on the next window. We're wanting this one here, aren't we? we want to calculate, oops, no, I've got hit the wrong one here. Oh, we do want that sometimes. Here we want the integral sign there. Meaning the sum of an infinite number of rectangles. Remember, that's where that curvy S comes from, skinny S. So we want that one. So we're going to hit F4 there again, and up comes the integral sign. Now this is very friendly because you can actually enter everything you need in the holes. This is Casier 9860 Plus, nice to use. So you can highlight one of those squares by hitting that button, and that will highlight the square and enter root x. And if you hit it again, and you can hit it that way or on the other side, it'll go to each of these squares in turn by navigating around with that key, that button, and put in 1 and 9, and then if you hit execute, you will come up with the answer. Okay, nice and handy. That's in run mode. Now you might have the graph on your screen, in which case you might like to do it in graph mode. So in graph mode, go to graph mode, enter the function, there it is, hit execute, so you've got the graph. Now once you've got the graph, you can go, let's do it over here, shift F5, which is G-solve, graph solving. We're solving the graph for various things. There's a lot of options on this window you can find, as you've done in earlier study, but you want to go to the next window, so you have to hit F6, and the next window has all of these little functions for you. There it is again, the integral sign. So you'll come down and hit F3. If you hit F3, the cursor will sit somewhere on your function. So you then hit any number. This is giving you a lower of x equals 5. So hit any number. I hit 1 because that's what we wanted, and up comes this window, just checking that you want to have a lower bound of 1. And so if you hit execute, then it switches to, it's got lower bound of 1, it switches to upper. If you then put in your upper bound, just hit the number 9. There it is, it checks that you want the upper bound of 9, hit execute, and oh, what do we got? Lower 1 upper, and there's the integral, the sum of an infinite number of rectangles drawn under the curve. They're making integrate, making a whole mass, summing the rectangles. Okay, powerful sign. We call it the integral sign because it's making one mass of it, and it looks like an S because it's reminding us sum of infinite number of rectangles there. All right, okay, can we go down and do something with this? Let's have a look. Here we are. Use the fundamental theorem of calculus. Find the area between the x-axis and y equals x squared cubed from x is 1 to x is 0. Check your answer with technology. So I think you should draw a graph of this. So you might go to graph mode on your calculator, just check out what the graph looks like, and then start to bring in the mathematical notation. Integral from 0 to 1 of x cubed dx equals, and then I think what you should do next is to actually find the antiderivative. We usually set it out this way. This is the area function, isn't it? The function which differentiated will give this one, and the only rule we're going to be using here for the minute is the x to the n rule. So in integrating, you increase the power by 1 and divide by the new power. Okay, might have to check e to the x down here. Integral of e to the x is itself, isn't it? Because its derivative is itself. And then we evaluate this from 0 to 1, and so on. Okay, we're evaluating that area function between the two values because we remember our special area function giving us that infinite rectangle sum has as its derivative the function itself. So we've got to go backwards, find the antiderivative. We're going to stop using that antiderivative idea shortly and say it's the integral. It is the function which when differentiated gives our original function, or the integral of the function. The wholeness, making all those rectangles one. Okay, pause the presentation, have a go. I'm going to take you down to the solutions here in a minute and see what you think. Okay, here are the solutions now to question 2. Here we have them. Okay, so pause that, have a look, make sure you're happy. These answers are given to all different number of decimal places. Usually we use 3 significant figures, unless otherwise stated, or the exact answer. Here are some exact answers. 3 3/4 is exact, quarter, etc. If it's not exact, you usually round to 3 significant figures, or as required. Okay, let's go on now. And here we have, you can see that we're going to have to do a lot of this. And when we find the antiderivative, that is the function, which when differentiated gives our given function, we are going backwards, and we're going to call this the process of integration. Okay, so because this function is crucial to the process of summing that infinite number of rectangles, isn't it? The fundamental theorem of calculus is this. Here we have it. Fundamental theorem. When we try to evaluate that infinite rectangle sum between A and B, taking the limit of the upper and lower rectangles, then we have to have this function, a function whose derivative is f of x, and we stick the numbers in there. We proved that earlier. That's the fundamental theorem of calculus. Now the process of getting this function now we're going to call integration. If we want to integrate our function with respect to x, we need this antiderivative. But we're going to get rid of that word now. We're going to call this the integral. Why do you think we put c here, plus c? Well, let's think about it. If we had f of x equals x squared, we'd say the integral of x squared with respect to x, what function differentiated gives it? It's x cubed on 3. Now if we evaluate it between 2 points, that wouldn't matter. But if we want absolutely the function which when differentiated gives this, there's a whole family of them. Because plus 2 when differentiated, derivative of 2 is 0. So we would still get from this, the derivative of this would still give us x squared, but so would any constant added on. Checking it. If it was plus 4, when we differentiate this, we would still get x squared back again. All of them would be the antiderivative or the integral. There's a whole family. Because when we back check, the derivative of 4 is 0, derivative of a constant is 0. So actually when we put this general expression, this is called the indefinite integral. We're not definitely evaluating it between 2 values and finding the area there. We're just wanting to look at the function whose antiderivative, or whose derivative is the original function we're working with. So we put plus c, because there's a whole family which when differentiated will give us x squared. So the antiderivatives form a big group, and we're going to try and do that process now so that we can use the fundamental theorem up here on any function. So what we're going to practice doing is just this. Can we get that big F of x? Okay, and then later we'll go back to areas in the second presentation here. So we better review this and see how difficult this is. Hey, when we get a function and we got its derivative, x to the n's alright, that was pretty simple. Constant times a function is a constant times its derivative. But the sum rule, yep, that's not too bad. If we had a whole lot of functions, x cubed, we could find the antiderivative or the integral of that. We could do them one by one. We could reverse each of those in a sum. But we're not going to be able to reverse the product and chain rule. You'd never be able to spot that, to go back, okay, to say, well, okay, this is the derivative of this function here, the antiderivative stuff. We won't be able to reverse those very easily. We will come to later on the chain rule, how to reverse that. E to the x should be okay. We don't know about these other functions down here though. 1 on x, we should be able to reverse that and say it was ln. The antiderivative of e to x is itself. Alright, so we don't know about these, so they're going to be interesting. What we're in the business now of reversing the process of differentiation. So really you're going to have to keep your head around this. Which way are we going? Alright, come down, let's start reversing some of these. Let's find some integrals. Let's do the easy ones now. If you had a function k, what would its antiderivative, or what's its integral now? Let's start using that. The integral is that function which when differentiated gives k back again. Let's check it. Derivative of kx plus c. Alright, derivative of kx is just k, using x to the n rule. Derivative of c is 0. Okay, so that worked. What about the integral of x to the n? Let's check. We have said that before. It's x to the n plus 1 on x n plus 1. So, and the derivative of the constant is 0. Let's check this. Okay, so it's 1 on n plus 1 times x to the n rule. n plus 1 times x to the 1 less power is x to the n. And the derivative of a constant is 0. Hey, that cancels. We do get x to the n back again. And what about e to the x, the integral of e to the x? Let's check this and see. The integral is such that when we differentiate it, we should get the function back again. Derivative of e to the x is itself. Derivative of c is 0. Yes, that works. And 1 on x. What when differentiated gives 1 on x? Let's check it. Is it ln mod x plus c? The derivative of that. The derivative of ln is 1 on x. Derivative of c is 0. Just notice we put this modular sign in, or absolute value sign, just reminding ourselves you can't find the log of a negative number. So you can, that function's only defined if you take the absolute value or modulus of x. So they are our easy starting tools. Why are we doing it? Remember the fundamental theorem. We have discovered something very exciting, and that is that the area function, when differentiated, gives us the function, when you do it in x's or t's, gives us the function we're working with, the area under its curve. Okay, so that's why we want to do this all the time. Can we do this to every function so that in finding the integral we can then go, and we're working with this area giving function now. Now, the important thing here is you must always add c. An arbitrary constant. It could be any constant. And it's called the integrating, or the constant of integration. I like that better. And it reminds us that there's a whole family, when we're doing this process, the family of functions that when differentiated would give that. So integration is finding indefinite integrals, not using the fundamental theorem, is finding that whole family. You must put in c there. Okay, come down and let's get started. Okay, here we have some. Find the integral. See, we're just using this sign now. We're meaning now a little bit different from the fundamental theorem. We want the function which when differentiated gives this. So we're going to find the reverse, and we write it like this. Increase the power, divide by the new power. Then this one, neg 2 lots of, increase the power, divide by the new power. Then 5 on differentiation. 5, it doesn't change with respect to x, is it? The differentiation is the rate of change. But we're not doing that, we're going backwards. So it is 5x. We want the function which when differentiated would give 5. And then don't forget, this is always 1 mark here. And you might say, oh, gee, it's only c, it shouldn't be worth 1 mark. But hang on, it's a whole concept. It's a whole concept. The concept is, this is a family. There's a family of possible functions which when differentiated will give my original function. Let's look at this one. We can't do those. We have to change them to x to the m. We must reverse a rule. So integration implies reverse a rule of differentiation. There isn't another way of actually calculating or working out this function. You must reverse a rule. So you must associate each part of the expression with a rule. And this is, of course, x to the neg 3, and root x is x to the half. Increase the power by 1. Check this. Neg 3 plus 1 is neg 2. And then divide by the new power. A half, increase the power by 1. A half plus 1 is 1.5, which is 3 over 2. That's the process we're doing. And then divide by 3 over 2. And just remembering here, a negative power, it means 1 over, so it goes down the bottom line. Dividing by 3 over 2, invert and multiply. Alright, plus c always on the end. It's a whole family of functions which when differentiated would give you that function. Let's come down and have a go. Here's some more. Okay. So at this stage now, with functions like this, we don't know anything about reversing this, so we're going to have to expand it all. First one squared, twice the product. Second one squared. Remember the rule. A plus b squared is a squared plus 2ab plus b squared. And then we're going to go on. 9x squared plus 12 plus 4x squared. All powers. Done. Then increase the power by 1, divide by new power. What is 12 the derivative of? 12x. Increase power by 1, divide by new power. Don't forget adding c. Once you've done the process, remembering that we have a whole family of functions, any ones differing by a constant will have the same derivative. So there we have it there. Alright, let's look at the quotient function. We've gone too far here now. I'll just go back up a bit. Okay, let's just go here and have a look at this second function. Okay, so that function is a quotient. There's no reversal of the quotient rule. Remember, with the integration, we're trying to find a function whose derivative is this, so we must divide it into both parts and come down to a simple x to the m power. So it's x squared on root x, take 2 on root x, and root x is x to the half, so you subtract the powers. 2 take a half, 3 over 2, and then this is x to the neg half here, x to the half in the denominator. Increase the power by 1, 3 over 2, let's check it. 3 over 2 plus 1 is what? 2.5, or 5 over 2, want to do it that way. And then divide by 5 over 2, increase neg a half by 1, neg a half plus 1 is a half, and divide by that. And don't forget, dividing by fractions, you invert and multiply. And you must have the constant of integration every time. Here's the rule that we're using. Reversing the differentiation, calling it now the general integral, increase the power by 1, divide by the new power. Okay, come down, and here's your first set. First set here, question 1 to 3, you're going well here. Hang on in there, think about it. Okay. So I suggest you might go through all of those actually. Okay, remember the integral sign means you must reverse a rule of differentiation. So you actually have to assign a rule to that type of function, saying, well, what sort of rule would produce that? I only have some tools here now, the x to the n, e to the x, 1 on x. We can reverse those, remembering that log, when differentiated, gives 1 on x. So integral of 1 on x is ln, or log. Okay. Pause it, have a go. The answers to these 3 questions just down below here. We'll just go down now. Let's miss that top bit there. Just come down here. Okay, there's question 1. Don't forget that C. C is important. It's a whole concept representing the idea that there's a family of functions, all which when differentiated will give that original function. Come down now. Question 2. Just might go a bit further with question 2 there. Just check your answers. Don't forget the C. Coming down. question 3. Okay, just remember the integral of 1 on x. What function gives you on differentiation 1 on x? It's ln. But you must put that modular sign in to ensure that the function ln is defined. ln is only defined on positive values, so absolute value there. All right, mark your work. Let's go on. We've got a lot of functions to reverse this process for. Now that we've found that the area-giving function has its derivative equal to the function, we've got to go and reverse all our differentiation rules so that we can use this stuff. The constant of integration can be found if we're given a point on the curve. Okay, let's say we have here the derivative is that. We want to get the reverse of that, go back to the function, so we're going to integrate it. There it is, integrate that function. And we get plus c. Well, that's not a unique function, that's a family, isn't it? There's a family produced by this process of integration. But if we stick x is 0 and function is 2 in here, so we know when you put x is 0 in these holes, the function should give you the value 2. We can put it in those holes and put it equal to 2, and so we know we have a unique function. So you can actually substitute in a known point and find a unique function. All right, let's come down, have a look. So here's some functions for you. The derivative is given, so you want the original function. So that's the antiderivative. No, we're going to call it the process of integration. So if you integrate a derivative, you get the original function back again. Well, we've got to put plus c here. We don't know what the function is. We have the basic form, which when differentiated we give this, but they could all differ by a constant and so all give the same derivative. Alright, so try each of those. I think you should do all of those. Here's the information at the end which will enable you to sub into the family function you get and find the unique c. Let's go on now and have a look at the answers. Okay, so there we have question 4. With our little evaluations at the end, substituting in the given information and the function value so that we can come up with a unique function. Okay, let's move on to the next variation, and here it is here. What if they've asked if we've got the second derivative? Oh, we've got to reverse the process twice. We've got to integrate twice to find the function. Okay, let's do it. The second derivative is this, and we know the first derivative when x is 0 gives value -1. So let's integrate this function. So I haven't put that in. I'd like to have a step f dash x is the integral of 12x squared take 4 dx, and then do the process. Increase the power of 1, increase power by 1 divided by new power. Integral of -4 is -4x plus c. Now substitute in, so there's the function. We're given him some information. F dash order is -1. So let's put 0 in place of x. 0, c has to equal -1. So c is -1, and we've found the actual derivative, not just the family. Now we want to integrate that, so I'd like to have a working step in here. F of x is the integral of 4x cubed, take 4x, take 1 with respect to x. So do it, increase power by 1 divided by new power for all these. -1, what would produce that on differentiation? -1x plus d. Now, you must use a different letter, different symbol for the next constant. You can use C or D, or could use K, because in any one problem, if you use the pronumeral more than once, it means it's got the same value as before, and we don't know that. C has been used at -1. The constant here may well not be -1, so you shouldn't use the same letter. Okay, so let's now simplify that. We get this. then substituting in the fact that when x is 1, the function was 4. So putting 1 in all the holes for x here, we get 1, take 2, take 1, plus d is 4. And if you add this up, it'll be adding 2 to both sides, d is 6. So the whole unique original function was that one. So given enough information, our integral does not have to produce a family. We can determine the actual functions. Time to do some. So come down. I'd like you to set it out well here. So when you're trying to find f dash x, I think you should put down it's the integral of f double dashed x dx and put the actual function in there and show the steps. And here, of course, we're given 2 pieces of information so that we can actually evaluate that constant there and have a unique function. So I encourage you to actually do that now, and we'll pause the presentation there and show the answers down below there. So let's go down now. Let's go down and have a look at the answers there. That's question 5. Okay. Let's go on and see if we can actually come centre screen now. Let's go on and see if we can look at doing some other rules. We've got a lot to do. We're trying to do the integral of every type of function we possibly can, so that we can use the fundamental theorem of calculus on any function we like. Okay, let's have a look. Let's reverse this one. When you differentiate e to the ax plus b, what happens? Derivative of e to the ax plus b is itself, but you must multiply by the derivative of this function up here. That's the function of function or chain rule, where you have f of g of x. The derivative of all of that is f dashed g of x times g dashed x, isn't it? So here, what are we going to have to do when we are integrating or finding the function whose derivative is keep e to the ax plus b the same and divide by the derivative. Okay, let's just check it. Let's just check here that if we differentiated this back again, would you believe that it worked? Okay, derivative of this part, it's 1 on a, lots of the derivative of this, which is e ax plus b, derivative of e is itself, times a, plus 0 for the constant. Yes, it works. You must divide by the derivative of that second function. So we're looking at that one up there. What about ax plus b to the m plus 1? Derivative of that is m plus 1 ax plus b to the n, and you must multiply, I prefer to put that down the end here, but you must multiply by the derivative of this second function. It's a function of function or chain rule again. So when you're going in reverse now, what are you going to do? Well, here's our function. Increase the power by 1, divide by the new power, and also divide by the derivative of what's in here. So we have a function of a function rule being reversed here for simple linear functions. Okay, it only works if the derivative of what's in here is a constant. And we'll come and see that later on. Don't forget the c's here. Okay, and you obviously can't have n equal to -1. You can't be dividing by 0. Come down and practice some more now. Let's have a look. Consider the derivative of ln ax plus b. Now, the derivative of that is 1 over ax plus b times the derivative of that, which is a. Well, usually we probably write it in stages. Derivative of ln is 1 over times a. Okay, so if we're going in reverse, what are we going to do? We spot it's a reciprocal, so it's ln ax plus b, but we divide by the derivative. So with this process of integration, we're dividing by the derivative of that second function, not timesing by it, because we're reversing that rule of differentiation. Okay, and we should put this absolute value or modulus sign in here, remembering this ln is defined only for positive values. In other words, ax plus b must be greater than 0. To ensure that, we put the absolute value around that part of the function. Okay, so you reverse the function, 1 on ax plus b, reversing that to ln, and then dividing by the derivative. Because differentiation would do the process and then times by the derivative. Okay, let's go down and have a look at an example. Here's the first one. So write down the integral, saying that you're reversing that process. Increase the power by 1, divide by a new power, and also divide by the derivative of that, or times by a half. And plus c, there's a whole family that when differentiated would give this function. Alright, and then our final statement. Let's look at the next one. This one here, we change it to a power first of all. Now, we'll increase the power by 1, divide by a new power, and divide by the derivative of the second function. Just keep in mind, it's a chain rule. There's function 1, and in there is function 2, if you like. Think about it like that. Dividing by -2 or multiplying by -1/2. And then, of course, dividing by this half, invert and multiply. Let's do it. (1/2) out the front times 2/1 comes to (1), and the half is probably best written as the root. Particularly if you're going to use the fundamental theorem and evaluate across an interval. Alright, let's come down. Here's some problems for you. I think we've got 3 there in 6E3. I think we need to look at each of those. If there are powers involved, like here, use a negative exponent, fractional and negative exponent, thinking about that, and a fractional or rational power there for the cube root. Okay, go through each of them and see what you think. Okay, you've got to watch these down here, because that's not ax plus b, this one and this one. You can only use that process and this one, so you might have to expand those. Remember, the integral of ax plus b to the n with respect to x is ax plus b to the m plus 1 divided by m plus 1 and also divided by a plus c, only if this is linear. You actually can't divide by a function in x there, because you would be generating a quotient, wouldn't you? And that would be an illogical loop. You wouldn't then use the functional chain rule to go back. It would not work, if you like. So you can only use this idea for linear functions in there. Otherwise you generate a quotient. So these I've got here will need to be expanded. You cannot divide by 2x, because that would then be a quotient rule, and you are presuming there with your integration that the rule used was function of function. You can check it out and see whether it works or not. Okay, have a go. You need to do most of those. Right, coming down, some answers here. Question 1. Don't forget the C. C is very important. There's a whole family which, when differentiated, would give these. Go down to the answer to question 2 now. Question 2. And then question 3. Right, let's look at another example. We've got to be able to do this to any function that comes along. Let's do another one. Integral of e to the 2x take 1. Okay, write it like this. Integral of e is itself. No change here. Then we must divide by the derivative, not multiply, like with differentiation, and then add c. Okay, let's look at another one over here. Integral of 2e to the 2x. Integral, you've got two lots of the function, so you've got two lots of its integral. The integral of e to the 2x is itself, because its derivative is itself, but then we must divide by the derivative of this function up here. It's a function of a function. That's a little bit different from differentiation. We multiply by the derivative. Here we're going to divide by the derivative to reverse that process. So here, integral of e to the neg 3x is itself. Then we must divide by the derivative of this function, which is neg 3. So it's neg a third there. That negative there is just continuing down, plus c. Don't forget the c. And then state the final answer. Negative times the negative is positive there. Okay, what about the last one? Integral of 4 over 1 take 2x. You put the 4 out the front, saying it's 4 lots of the integral. You're not actually integrating the constant, you're saying it's 4 lots of the function. So it's 4 lots of the function's integral. That's 4 lots of 1 over. That's ln, but you must ensure that it's going to be loggable, if you like, and take the log. So you put the absolute value. So ln of 1 take 2x, but then this is itself a function x, or all of this, sorry. The thing that you're finding the log of is all a function in x. You have to now divide by the derivative of that, which is neg 2. So put 1 over neg 2. And then simplifying that, and plus c, of course, on the end. So you must identify a rule. A rule of differentiation to reverse. You've got to say, hey, that's been done here, I'm going to reverse it. Because that's our notion. We're finding a function whose derivative was the original function. All right. Come down. So we'll look at some questions. Question 4, 5, 6 and 7. This is an interesting one. Have to think about this. Think about the constants of integration there. All right, have a go. I think you should do most of question 4. Maybe a couple of parts. Question 5, question 6. Certainly. Interesting. Try and do all of them. Okay, come down now. Questions 7, 8 and 9. And the answer's coming up now. 4. 5 and 6, part of 7. That's all of 7 now. And 8 and 9. Okay, let's go down to the final one in this course that we do. Integrals of the form f of u du by dx dx. What are they talking about there? Well, let's have a look at an example that you might be able to recognise. Integral of, let's say, 3x squared plus 4 cubed times 6x dx. Can you see the pattern they're talking about? You have some function in u. In other words, it's a chain rule, isn't it? It's a function of another function and its derivative is present. What they're trying to say here is we are reversing the chain rule, where we have the power function done on another function and then its derivative is present. So it's a matter of here recognition of the chain rule being applied, or the function of function rule being applied. Recognition of the chain rule. So you will have a chain of derivatives. You can expect something, maybe to a power here, and then this thing here will be the derivative of that. That's what they're saying. That's what this statement is saying. You have a function in u, which is a self-function in x, then the derivative of that function, and you're doing an integration across the lot. So let's have a look. Suppose f of u is the antiderivative of f of u. So derivative of f of x is f of u. Now, the derivative of f of u is the derivative with respect to u of f of u times derivative of u with respect to x. That's doing the two parts. Taking this function, ignoring that, then timesing by the derivative of it. We then differentiate the first function and then multiply by the derivative of that internal function in f. Okay, but df by du is f of u. So there we have the derivative of f of u is f of u du by dx. So we're going to say here the integral of f of u du by dx is our original function, which is the integral of f of u du. A bit hard to follow that. In words, it's saying when you have a function and its derivative with respect to x is accompanying it, so you have an accompanying derivative, so it's like a product, but it's a special product. That's the derivative of what's inside f. Then all you've got to do is integrate f to big F. And of course you'll have an expression there in u which is in x. So it's recognition of the chain rule. You're looking for a function and its accompanying derivative. Let's have a look at what it looks like as a problem. Here's a good one here. So let's say we're given this, the integral of this. Now it stands out because we don't integrate a product easily here. U dash v plus uv dash. How would we recognise that? So where would this product come from? Oh, this is certainly a product, but it's not of that u dash v plus uv dash form. Oh, but it's a function of function, isn't it? There's a function done on this little function, and what do you notice? This little function's derivative is there. Excuse me. So it is of the form, the integral of what? F of u du by dx with respect to x. We have a function and its derivative is present. That looks as if the chain rule has been applied. Let's prove it. So we let u equal the function in here. Okay, so the idea is you let u be the function whose derivative is present. That's the idea of letting u. You can't let u be u to the fourth. Okay, let's go back and look at this then. So when we're deciding u, we see it's a product and this is the derivative of this thing here. So that's going to be u. So over here we say let u be that, differentiate it. 2u du by dx is 2x plus 3. Now we'll put it all in u land here. What have we got? We've got u to the fourth, its derivative present with respect to x. We know that this derivative is present from the chain rule. So all we have to do is reverse the other function. That's what it's saying. Reverse u to the fourth. So it's u to 5 on 5. We don't have to worry about this. We just have to worry about this function. That's what it's saying. Why is this here? Because it's a derivative of that in there. It's saying you can ignore that derivative. It's come about through the application of the chain rule, and all we actually have to reverse is the function in front and add c. And then we put back x squared plus 3x. So we're breaking it down to the crucial variation that we're looking at there. And that is the function f there of 4. Okay. Do we need to do another one? I think we'll just come down here and have a look at another example. So, use substitution. Yes, this method is called the method of substitution, but really it's the recognition of the chain rule being applied. And we're going to prove that recognition by using substitution. Let's have a look at this pair over here. This is a product. So you're immediately suspicious. We do not integrate a product. The product has probably come from the idea of the chain rule. Yes, this is the derivative of this. So let u be equal to x cubed plus 2x. I wouldn't set it out quite this way. We would say then du by dx is equal to 3x squared plus 2. and then put this in. The integral is the integral of u, there's u, to the half, du by dx dx, which we can say, now we don't cancel that. You can think of that, but it's saying we have a pattern here, we're trying to recognise a chain rule. There's a function of a function, there's its derivative. Oh, it's a chain rule. That's what they're saying here. The theorem then says all you have to integrate is the first function. This is popped up by finding the derivative of u with respect to x. All you have to do is actually look at the variation of the root function with respect to this. This is then being differentiated, and you don't have to worry about the integration of that. So increasing the power by 1, dividing by the new power, and that becomes 2/3, dividing by a fraction, invert and multiply, and then returning u to x cubed plus 2x. Don't forget the c on the end. So the substitution is come right up the top here. It's trying to prove a recognition of the chain rule and saying all we really have to do is worry about the variation of the first function, okay, with respect to what's in the middle of it there. Okay, let's have a look at this. A quotient. We can't integrate a quotient. So let's change it to a product. 1 over x cubed plus 2x by this. We can't integrate a product unless it's a product of derivatives coming from the chain rule, is it? Oh yeah, that's a derivative of this little thing down here. So let u equal x cubed plus 2x. Put this down to u by dx equals 3x squared plus 2. Then put this. The integral is equal to the integral of 1 on u to u by dx dx. So you can write it as here then put this in, and then put the integral is the integral of 1 on u to u by dx dx, so it's got some continuity, and then you can say that's the integral of 1 on u. What we're saying is we can ignore the variation of this with respect to x. We're looking at how 1 on u, that function, the 1 on, is varying with respect to that variable. Okay. 1 on u, oh, I recognise that. 1 ons come from the differentiation of ln. So it's ln mod u. Remember, don't forget the modulus because you can't find the ln of a negative number, plus c. And then return to xlan. The u substitution is called integration by substitution, is to prove the association with the chain rule and validate your process. Let's look at this. This is a product. So you are suspicious. Is this the derivative of this function? Yes, almost. Hang on, we better have a look. They've got it here. Let u be equal to 1 take x squared. I put it up here. Du by dx is neg 2x. Uh-oh, so you better do something here. Therefore, you've only got x in there. X is neg a half du by dx. And then you get this. I think they've skipped a couple of steps here. So I would then say, I put my integral down, therefore, the integral of x, e to the 1 take x squared dx is equal to the integral of e to the 1 take x squared. Now what's x? It's neg a half du by dx. And with respect to x. So I would rearrange the du by dx to get your x term. And then in the original expression here, that x is replaced by that. Then you have neg a half integral of e to the 1 take x squared du. Oh, sorry, e to the u, then up there we can put the u in after that, du by dx. So, they have done a few steps all in here together. I think the important thing is to isolate x because some of them get complicated as to what that other term is. So this term out the front, check if it's not a perfect derivative of the other one, rearrange the derivative statement to get it and substitute it in. So we go to this line and integrating e to the u is just itself. and then returning to xland there with a constant as soon as you do that process. The setting out here is important to prove or validate what you're doing. Alright, time for some problems. Let's have a look at these. This is coming to the end of this first part, because the next part is applications of integration, but we have to have our skills up so we can do this integration process. There's question 1 and 2. I think just part of 3. No, that's all of 3. So have a go there. We'll just go down to question 4. And then the solutions are coming on underneath. Question 1. Rest of question 1, just missing that last bit out there. Let's come up a bit more. Okay, going to question 2. Let's go down a bit more. Let's go on now. Question 3. Most of it. We've got a little bit more coming up. Question 3 and parts of 4 there. Let's just see if we can get them on. Okay, question 4. Okay, and that's the rest of question 4. Okay, now you've got some good skills you've built up there. Now we want to say, what are all the uses we can put them to? Obviously areas are a big one, but there's some motion problems and stuff we can do also. So keep working hard on practice, and it's cheers for now, but I'll catch you in the application section. Cheers.